Thermodynamics, in its generalized sense, is about the theory and study of how energy transforms matter within all physical systems, from the formation of stars to photosynthesis to the running of your car. The laws of thermodynamics are central to understanding ecosystems by the nature of their physical state. With a solid understanding of thermodynamic principles, we can begin to create abstract and rigorous models to the complete energy and material flows through an ecosystem. Thermodynamics is a very exciting area of physics because although the theory of equilibrium thermodynamics is well understood, the thermodynamics of systems far from equilibrium remains very much an active area of research. Thermodynamics is the branch of physical science concerned with the interrelationship and interconversion of different forms of energy, in particular thermal energy. On a more generalized level, we might say it is the study of how energy transforms matter through processes, the structures or order that emerges out of those transformations, and how we can describe these states of order and disorder in terms of information and the capacity to do work. Put energy into a system and that system will respond. This is the nature of a thermodynamic driving force. It is a way to push and pull on a material, to alter its state and structure with any type of energy. By applying some energy, the system responds. Apply a pressure and see the volume change. Increase the temperature and watch the material melt. Decrease it and watch it solidify. One of the great benefits to having thermodynamics as the theoretical underpinnings to systems ecology is that it applies equally to physical, biological, and engineered systems, giving us an integrated framework for the rigorous modeling of both ecosystems and industrial economies, often in a quantitative fashion if need be. Through thermodynamics, we can see that the same processes shape both the development of ecosystems and our technology infrastructure, and it is through this understanding of thermodynamics that we have engineered our physical environment. Through understanding this process, we first learned to cook, we learned to shape metals through smelting, to produce steel. By understanding the subtleties of these thermodynamic processes, we could create different types of steel by regulating how rapidly the molten metal is cooled into a solid. It is through this understanding that we learned to make engines that turn heat into mechanical work, to make electricity from spinning turbines, and to make plastics of all kinds. We obviously don't have time for a full discussion of thermodynamics here, but we'll firstly give an outline to equilibrium thermodynamics and its basic laws, before going on to talk about non-equilibrium thermodynamics, and in particular dissipative systems. Equilibrium thermodynamics, as a subject in physics, considers the macroscopic bodies of matter and energy in states of internal thermodynamic equilibrium. Thermodynamic equilibrium is characterized by an absence of the flow of matter or energy. More generally, equilibrium is a state where the system will not change unless given some perturbation from its environment. Isolated thermodynamic systems, if not initially in thermodynamic equilibrium, as time passes, tend to evolve naturally towards this equilibrium. In the absence of externally imposed forces, they become homogeneous in their local properties. This condition of equilibrium is really enshrined in the zero law of thermodynamics, which states that if two systems are each in thermodynamic equilibrium with a third, they are also in thermodynamic equilibrium with each other. The zero law is clearly a statement of equilibrium, and it is this equilibrium through which we define the measurement of temperature as that which ceases to flow between systems in thermal contact. The first law, in its generalized sense, is a statement of the conservation of energy in matter. It posits that energy can never be created or destroyed, but it can be transformed from one form into another. This implies that the total energy of an isolated system remains constant over time. The first law tells us about the flow of energy within a physical system, and that we can trace this transformation from one form to another through the system. The second law of thermodynamics is an expression of the universal principle of dissipation to kinetic and potential energy observed throughout nature. The second law is an observation of the fact that over time, differences in temperature, pressure, and chemical potential tend to even out in a physical system that is isolated from the outside world. The entropy of an isolated system that is not in equilibrium tends to increase over time, approaching a maximum value at equilibrium. Entropy is a measurement of the number of degrees of freedom a system has. Take the example of a perfect crystal, in which case the atoms are all locked into rigid positions in a lattice formation, so the number of ways they can move around is quite limited. In a liquid, the options increase considerably. In a gas, the atoms can take on many more configurations. This is why the entropy of a gas is higher than liquid, which is in turn higher than a solid. When the entropy goes up, it requires more information to describe the state of the system, and it would require more work to be done in order to reconfigure the system into its original ordered state. As such, entropy is a key measurement in information theory, where it quantifies the uncertainty involved in predicting the value of a random variable. The second law states that whenever energy is converted from one form to another, some of the energy becomes low-level heat. This means that the conversion of energy from one form to another is never 100% efficient. Some of the energy is lost as heat. The lost energy is still energy, but it's no longer high-level energy that can be used for work, such as moving things or fueling metabolic processes in plants and animals. Thus, the second law is one of the few, if not only, physical laws that differentiates between the directions of time. The third law tells us that as a system approaches absolute zero in Kelvin temperature, the entropy of the system approaches a maximum value, and that it is impossible to reach the absolute zero of temperature by any finite number of processes. The second law defines an increase in permutations and randomness over time. But biological systems are characterized by increases of order and complexity. As a result, it is often noted that biological systems must be functioning at a state far from equilibrium. This observation has led to the extension of standard thermodynamic theory through the development of what is called non-equilibrium thermodynamics, a recognition that standard thermodynamics only really applies to systems at, near, or moving towards some equilibrium. It is therefore legitimate to ask to what extent equilibrium thermodynamics can be generalized to cover more general situations of non-homogeneous systems, far from equilibrium states and irreversible processes. Many efforts have been spent to meet such objectives and have resulted in the development of various approaches coined under the generic name of non-equilibrium thermodynamics. Most systems found in nature or considered in engineering are not in thermodynamic equilibrium. They are changing or can be triggered to change over time, and are continuously subject to flux of matter and energy to and from other systems. Equilibrium thermodynamics restricts its considerations to processes that have initial and final states of thermodynamic equilibrium. The time course of processes are deliberately ignored. But with far from equilibrium systems, the forward and reverse reaction rates no longer balance, and the concentration of reactants and products is no longer constant. Damping of acoustic perturbations or shock waves are non-stationary, non-equilibrium processes. Driven complex fluids, turbulent systems, and glasses are other examples of non-equilibrium systems within physics. Whereas standard thermodynamics describes systems that have a relatively low exchange with their environment, making them relatively closed. Non-equilibrium thermodynamics is dealing with systems that are, in a generalized sense, more open than closed, having an almost continuous exchange with their environment, meaning we cannot just describe them as moving from one equilibrium to another, but we now have to interpret them in terms of constant change, flux, or flow of resources from the environment through the system. To recognize the difference between equilibrium and non-equilibrium, we can think about a ball at the bottom of a bowl. This is a system in equilibrium. Now imagine this ball rolling down a hill. It is now in a state of disequilibrium. There is a constant input or release of energy from the system as it travels across a gravitational potential gradient. In this process, we can say that its potential energy is being dissipated. But this ball is really just traveling from one equilibrium to another. It will get to its lowest gravitational potential energy sooner or later and then just stay there. To get a truly non-equilibrium system, we would need one that is continuously traveling across some energy gradient, continuously dissipating energy in the process. This is a dissipative system, and it is exactly what biological creatures do. From a thermodynamic point of view, this is essentially what defines biological creatures. They are able to maintain themselves far from equilibrium by accessing free energy and dissipating it and reiterating on this process. In so doing, continuously traveling across some potential energy gradient. Dissipative structures are open systems. They need a constant input of free energy from the environment in order to maintain the capacity to do work. It is this continual flux of energy in and out of a dissipative structure which leads towards self-organization and ultimately the ability to function at a continuous state of non-equilibrium. A famous example of a self-organizing dissipative structure is the spontaneous organization of water due to convection. If we take a thin layer of water at uniform temperature and start heating it from the bottom, a pattern starts to emerge. As the temperature between the bottom and top of the water reaches a critical level, the water begins to move away from an equilibrium state and an instability within the system develops. At this point, convection commences and the dissipative structure forms. As heat is transformed through the liquid, a patterned hexagonal or honeycomb shape emerges called Bernard cells, and the capacity to do work is realized. But as soon as the energy source to the heat is taken away, the ordered pattern disappears and the water returns to an equilibrium state. Just like the convection of water, biological organisms are also self-organizing dissipative structures. They take in and give off energy to and from their environment in order to sustain life processes and in so doing function at a state of non-equilibrium. Although biological organisms maintain a state far from equilibrium, they are still governed by the second law of thermodynamics. Like all physiochemical systems, biological systems are also increasing their entropy as part of the overwhelming drive towards equilibrium. In order to avoid this move towards equilibrium, they have to maintain themselves on some energy gradient. Just as the input and dissipation of energy within the water in the pan enabled the formation of non-equilibrium patterns of convection cells, it is the constant input and dissipation of energy that enables biological creatures to exist far from equilibrium. Open, dissipative systems make an effort to avoid a transition into thermodynamic equilibrium by a continuous exchange of materials and energy with their environment. According to the theory of dissipative structures, an open system has a capability to continuously import free energy from the environment and at the same time export entropy. The internal structure and development of dissipative systems, as well as the process by which they come into existence, evolve and expire, are governed by the transfer of energy from the environment. Unlike isolated systems or closed systems in a broader sense, which are always on the path to thermodynamic equilibrium, Dissipative systems have a potential to offset the increasing entropy trend by consuming energy and using it to export entropy to their environment, thus creating negative entropy or negentropy. This prevents the system from moving towards an equilibrium state. A negentropic process is, therefore, the foundation for growth and evolution in thermodynamic systems. It can be said that order in an open system can be maintained only in a non-equilibrium condition. In other words, an open, dissipative system needs to maintain an exchange of energy and resources with the environment in order to be able to continuously renew itself. For dissipative systems to sustain their growth, they must not only increase their negentropic potential, but they must also eliminate the positive entropy that naturally accumulates over time as systems are trying to sustain themselves. The build-up of the system's internal complexity as it grows is also accompanied by the production of positive entropy, which must be exported out of the system as waste or low-grade energy. Otherwise, the accumulation of positive entropy in the system will eventually bring it into thermodynamic equilibrium, a state in which the system cannot maintain its order and organization. In other words, this is what we call death within a biological system. Of central interest within non-equilibrium thermodynamics is then the idea of a potential energy difference or gradient across which the system exists, and this idea is captured in the term exergy. Whereas energy and entropy are central concepts within standard thermodynamics, the idea of exergy is central to non-equilibrium thermodynamics and systems ecology. It is a measurement of both the system and its environment, more specifically a measure of how the system departs from its environment, the maximum amount of work that can be done before the system comes to equilibrium with its surroundings. As such, exergy is a measurement of the potential for usefulness. Because biological systems are largely defined by this capacity to maintain themselves far from equilibrium, we can theoretically understand how alive they are by asking how far from equilibrium they are. This is what exergy tries to capture. As such, it is often used as a basis for the analysis of the health or resilience of an ecosystem. When exergy is zero, the system is in equilibrium with its environment, which would equate to the complete collapse of an ecosystem. Whereas most of the laws governing thermodynamic systems are theoretically time reversible, dissipative processes are path dependent and irreversible. A non-equilibrium state needs for its description time and space dependent state variables. Because of the exchanges of mass and energy between the system and its surroundings, an irreversible process is one in which free energy is dissipated. How the process was performed comes to matter. This time irreversibility is closely related to efficiency. The destruction of exergy is closely related to the creation of entropy, and thus any system containing highly irreversible processes will have a low energy efficiency. As an example, the combustion process within a power station's gas turbine is highly irreversible, and approximately 25% of the energy inputted will be destroyed in the process. In this module, we've been briefly outlining the basics of equilibrium and non-equilibrium thermodynamics that forms much of the theoretical underpinnings to systems ecology. We firstly defined thermodynamics in a very broad sense as the theory and study of how energy transforms matter through processes. We then went on to talk about the 4 laws of equilibrium thermodynamics. We discussed non-equilibrium thermodynamics as dealing with systems that are more open than closed, having an almost continuous exchange with their environment, where we now have to interpret them in terms of a constant exchange, flux, or flow of resources from the environment. We talked about the theory of dissipative systems that maintain themselves on some energy gradient allowing them to maintain a semi-stable state far from equilibrium, importing energy and exporting entropy, a dynamic that is characteristic of biological systems of all kind. Finally, we discussed the idea of exergy as a metric for measuring this out of equilibrium state and the vitality of an ecological system.